Fermat's last theorem, the generalized difference of powers equations, Part 1. My motto, plain honesty, simple truth, easy understanding, the joy of finding things out for yourself. 1. As is widely known, the Fermat equation, c to the n equals a to the n plus b to the n, rearranges to give 1. C to the n minus a to the n equals b to the n, and 2. C to the n minus b to the n equals a to the n. So if we can generate an all-encompassing set of equations for 1 and 2, then the equations apply equally to all integers and all powers for all differences of two powers, whether they are a Fermat equation or not, and therefore have big implications for the existence or otherwise of a Fermat triple. 2. So considering the following identities and taking 1 and expanding by a long division, we obtain the following equations for the differences of the powers. These are the so-called binomial number equations that were briefly mentioned by Robert Carmichael in his 1915 paper Diophantine Equations, and a good account can be found on Wolfram MathWorld. Despite their importance, they are rarely, if ever, brought to one's attention by the modern practitioners of mathematics. I wonder why. 3. Taking the identity 1, we replace x by y plus 1, y plus 2, y plus 3, y plus delta, so that the denominator x minus y equals y plus delta minus y is equal to delta, which is equal to 1, 2, 3, 4, all the way to infinity. We thus proceed as follows for every power. 4. X squared minus y squared equals x plus y all multiplied by delta is equal to y plus delta plus y all multiplied by delta equals 2y plus delta all multiplied by delta equals 2 delta y plus delta squared, the basic equation. So we get the following equations for different delta and y equals 3, which can be continued ad infinitum. 5. X cubed minus y cubed equals x squared plus xy plus y squared all multiplied by delta, which leads to the basic equation 3 delta y squared plus 3 delta squared y plus delta cubed. So we get the following equations for different delta and y equals 5, and the equations can be continued all the way to infinity. 6. X to the power 4 minus y to the power 4 equals x cubed plus x squared y plus xy squared plus y cubed all multiplied by delta, which leads to the final basic equation 4 delta y cubed plus 6 delta squared y squared plus 4 delta cubed y plus delta to the power 4. The intermediate steps have been color-coded to show how the terms of the final basic equation have accumulated. So we get the following equations for different delta and y equals 5, and we can see that these can be continued ad infinitum all the way to infinity. 7. We note that coefficients of the basic algebraic equation obtained for each power are the same as those that are given by Pascal's triangle, minus the first coefficient, which is always 1. 8. It is plain for all to see that all powers are the sum of two specific powers plus n-1 terms of lower degree, as given by the two following examples. 1. 11 cubed is equal to 5 cubed plus 450 plus 540 plus 11 minus 5 all cubed is equal to 1331. 2. 9 to the 4th equals 5 to the 4th plus 2000 plus 2400 plus 1280 plus 9 minus 5 all to the power 4 is equal to 6561. 9. If for any power we sum the terms of lower degree, we find a. that the summed integer divides by the base number of the power that was subtracted, b. that repeatedly differencing the adjacent dividends obtained will always result in a constant difference, which is the factorial of the power. See the following table. (10) Finally, since proof is truth, then likewise truth is proof, and which with regard to the absolute truth of statement 8 means that Fermat's marginal note he wrote 350 plus years ago was absolutely correct, and that he did indeed have the tools, contrary to modern opinion, to come to his famous conclusion. So it seems to me that the quest for the modern proof was nothing but a fool's errand.